Hello everyone, and welcome to Sleep and Learn. Tonight, we're exploring one of the most fascinating questions in the universe. How far could a human travel through space in a single lifetime? From the limits of modern spacecraft to the mind-bending effects of time itself, this journey will take you beyond imagination and into the deep, quiet mysteries of the cosmos. Get comfortable, relax, and let's begin. The real limits of human space travel. Take a slow breath in and gently let it go. Before we imagine crossing galaxies, we must begin with a simple, grounding truth. Space is not just big, it is unimaginably vast. The distances between stars are so enormous that even our fastest machines barely make a dent in them. Right now, humanity's most distant ambassador is Voyager 1. Launched in 1977, it has been traveling for nearly half a century and is now over 24 billion kilometers from Earth. It sounds impressive, and it is. But in cosmic terms, it has only just stepped outside our front door. The nearest star system, Alpha Centauri, lies about 4.37 light-years away. A light-year is the distance light travels in 1 year, about 9.46 trillion kilometers. Even at the incredible speed of Voyager 1, it would take over 70,000 years to get there. This is the first barrier: distance. The speed limit of the universe. At the heart of all cosmic travel lies a fundamental rule described by special relativity. According to this theory, nothing with mass can reach or exceed the speed of light. Light travels at about 299,792 kilometers per second. That's fast enough to circle Earth more than 7 times in a single second. But for anything made of matter, like a spacecraft or a human body, reaching that speed would require infinite energy. This is not a technological limitation. It is a law of nature. Even approaching the speed of light becomes increasingly difficult. The closer you get, the more energy you need for even the smallest increase in speed. It's like trying to climb a mountain that becomes steeper the higher you go. Eventually, the climb becomes impossible. How fast can we actually go? The fastest spacecraft ever built, the Parker Solar Probe, reaches speeds of about 700,000 kilometers per hour at its peak. That's fast enough to travel from New York to Tokyo in under a minute. But even at that speed, reaching Alpha Centauri would take more than 6,000 years. To put this into perspective, human civilization itself is only about 10,000 years old. A journey to the nearest star would outlast recorded history. The problem of human lifetimes. A typical human lifetime, let's say 80 to 100 years, is incredibly short compared to cosmic distances. Even if we could build a spacecraft capable of traveling 10 times faster than anything we have today, interstellar travel would still take centuries or millennia. This introduces a fundamental challenge. How can a human experience a journey that takes longer than their entire lifespan? There are a few theoretical solutions. Generation ships, where multiple generations live and die during the journey. Cryogenic sleep, where travelers are frozen and awakened upon arrival. Artificial intelligence missions, where no humans travel at all. But all of these come with enormous technical, ethical, and biological challenges. And none of them truly solve the deeper problem: time itself. Space is not empty. Another surprising truth is that space is not completely empty. It contains sparse atoms, radiation, and high-energy particles traveling at nearly the speed of light. At low speeds, these particles are harmless. But as a spacecraft approaches relativistic speeds, close to the speed of light, these tiny particles become dangerous. A single atom can hit a spacecraft with the energy of a bullet. Over time, this constant bombardment could damage or even destroy the ship. This means that high-speed travel isn't just about propulsion, it's also about protection. The invisible obstacles. Beyond physical particles, there are other hidden challenges. Radiation exposure. Cosmic rays can damage DNA and increase cancer risk. Isolation. Long-duration missions can affect mental health. Resource limitations. Food, water, and oxygen must be sustained for years or decades. Mechanical failure, even a small malfunction, could be catastrophic far from Earth. These are not science fiction problems. They are real engineering challenges that scientists are actively studying today. Organizations like NASA and ESA are already researching long-duration spaceflight, but interstellar travel remains far beyond our current capabilities. A universe that resists us. When you step back and look at all these limitations together, a clear picture emerges. The universe does not make travel easy. Distances are vast. Speeds are limited. Time is short. And the environment itself is hostile. At first glance, it might seem like humanity is trapped, forever confined to a tiny corner of the cosmos. But this is where the story takes an unexpected turn. Because hidden within the same laws that limit us are the very principles that might one day set us free. In the next part, we will explore a strange and beautiful consequence of relativity, one that allows time itself to stretch and bend, and may offer a way for a single human lifetime to reach the stars. Time, relativity, and the strange expansion of distance. Take another slow breath in, and gently let it go. In the previous part, we reached a hard boundary of physics, the speed of light. But the deeper truth of space travel is not just about how fast you move. It is about how time itself behaves when you move close to that limit. Because in the universe described by special relativity, speed is not just motion through space, it is also motion through time. And this changes everything. Time is not the same everywhere. On Earth, we experience time as steady and universal. 1 second feels like 1 second for everyone. But in reality, time is flexible. It stretches and compresses depending on speed and gravity. This effect is called time dilation. If a spacecraft travels close to the speed of light, time inside that spacecraft slows down compared to Earth. To the travelers, everything feels normal. Their heartbeat, their thoughts, their aging, all continue normally. But outside the ship, centuries could pass. The paradox of interstellar travel. Imagine a ship traveling to Alpha Centauri at 99.9% the speed of light. From Earth's perspective, the journey might take over 4 years. But for the astronauts on board, it could feel like only a few months. If the ship could somehow reach even higher speeds, 99.9999% of light speed, the difference becomes extreme. A journey that takes 10,000 years from Earth's perspective could feel like only 50 years for the crew. This is not science fiction. It is a direct prediction of Einstein's equations. The shrinking universe. As speed increases, something even stranger happens. Distances begin to shrink, not physically, but mathematically. From the traveler's perspective, the distance between stars contracts in the direction of motion. This effect is called length contraction. To an outside observer, the universe remains enormous. But to the traveler, space itself seems compressed, as if the cosmos is folding inward to make the journey shorter. It is as if the universe is helping you move through it. The human cost of relativistic travel. But there is a hidden consequence. When a traveler returns to Earth after a relativistic journey, they find a world they no longer recognize. Thousands of years may have passed. Civilizations may have risen and disappeared. Languages, cultures, even humanity itself could have changed. The traveler becomes a time outsider, disconnected from their own origin. This is one of the most haunting implications of relativistic travel. You can reach the future of the universe, but you may never return to your own present. The edge of usable time. Even more unsettling is the fact that time dilation does not give unlimited travel freedom. It only shifts the experience of time, not the total energy required. To accelerate a spacecraft close to light speed still requires enormous energy, far beyond anything humanity can currently produce. Even advanced missions imagined by agencies like NASA and ESA are limited to small fractions of light speed. So while relativity offers a theoretical escape from distance, it does not yet offer a practical one. The universe becomes heavier as you move faster. Another strange effect appears as velocity increases. The faster you go, the more energy your motion requires. In fact, your effective mass increases. This means your spacecraft becomes harder and harder to accelerate. It is as if the universe is placing an invisible resistance on anything trying to reach the speed of light. No matter how advanced the engine, the final step to light speed remains unreachable. Why light is the only true traveler? Light itself does not experience time. From the perspective of a photon, the journey from a star to your eye happens instantly, no matter how far it travels. But this perspective is not something matter can share. A human, a ship, or any object with mass must always experience time passing. This is one of the deepest separations in physics. The universe is divided between light and everything else. A universe that bends, but does not break. When we step back, a strange picture emerges. Space is flexible. Time is flexible. Distance is flexible. But the speed of light remains fixed. It is the one unchanging rule around which everything else bends. And yet, within these constraints, the universe still allows something extraordinary. The possibility that a single human lifetime could stretch across cosmic scales, not by breaking physics, but by riding within its deepest rules. What comes next? If relativity is not enough to fully bridge the stars, then humanity must ask a more radical question. What if we do not travel through space at all? What if space itself could be changed? In the next part, we will explore one of the most controversial and fascinating ideas in modern physics, the possibility of bending space like fabric and moving the universe around a ship instead of moving the ship through the universe. A concept that begins to sound like magic, but still lives inside the equations of physics. Bending space, the possibility of warp travel. Take a slow breath in, and gently let it go. So far, we have followed the rules of the universe as they are, limits on speed, the stretching of time, and the strange shrinking of distance. But what if the real path to the stars does not involve moving faster, but changing space itself? Hidden within the deeper framework of general relativity is an idea so unusual that it feels almost like science fiction. Space is not rigid. It can bend, stretch, and even flow. Space is not empty. It is a fabric. According to modern physics, space and time are woven together into something called spacetime. Massive objects, like stars and planets, warp this fabric, creating what we experience as gravity. This means that gravity is not a force pulling objects together. It is the result of curved space guiding motion. If you could look at spacetime from the outside, it would resemble a flexible surface, bending under the weight of matter. And if space can bend naturally, then perhaps it can be bent intentionally. The idea of a warp drive. In 1994, a physicist named Miguel Alcubierre proposed a remarkable solution to faster-than-light travel. Instead of accelerating a spacecraft through space, his idea suggested something completely different. Move space itself. A spacecraft could sit inside a bubble of space-time. In front of the bubble, space would compress. Behind it, space would expand. This would allow the bubble, and everything inside it, to effectively move faster than light relative to the outside universe. This concept is now known as the Alcubierre warp drive. Breaking the rules, without breaking them. At first glance, warp travel seems to violate the cosmic speed limit. But it doesn't. Because the spacecraft itself is not moving through space faster than light. Instead, space itself is carrying the spacecraft. It's similar to standing on a moving walkway at an airport. You are not walking faster, but the ground beneath you is moving. In theory, this means a ship could cross vast distances, hundreds, thousands, even millions of light years, within a human lifetime. To an outside observer, the journey would still obey the laws of physics. But to the traveler, it could feel almost instantaneous. The energy problem. There is, however, a serious challenge. Warp drives require something known as negative energy. This is not just a large amount of energy. It is a completely different kind of energy that behaves opposite to normal matter. Negative energy would be needed to stabilize the warp bubble and keep it from collapsing. The problem is that we have never observed usable amounts of negative energy in nature. Some quantum effects, like the Casimir effect, hint that negative energy might exist in tiny amounts. But scaling this up to power a spacecraft would require technology far beyond anything humanity currently understands. The dangers of warping space. Even if we could build a warp drive, it might not be safe. Some theoretical models suggest that a warp bubble could accumulate high-energy particles as it moves. When the ship stops, this energy could be released in a burst, potentially destroying anything at its destination. There are also concerns about stability. A small disturbance in the structure of spacetime could cause the bubble to collapse unpredictably. And if that happened, the consequences would be impossible to control. The horizon problem. Another strange limitation appears when we look deeper into the math. Inside a warp bubble, communication with the outside universe may become impossible. The front edge of the bubble could act like a horizon, similar to the edge of a black hole. This means the crew might not be able to control the ship once the journey begins. They would be passengers, carried by a wave of spacetime they cannot steer. Is warp travel real? At this moment, warp drives remain purely theoretical. No experiment has come close to creating a real warp bubble. However, research continues. Scientists at organizations like NASA have explored simplified models, trying to reduce the enormous energy requirements. Some newer theories suggest that the amount of energy needed might be far smaller than originally thought, perhaps even within the realm of possibility for a highly advanced civilization. A universe more flexible than we imagined. What makes warp travel so fascinating is not just the idea of faster-than-light movement. It is what it reveals about the universe itself. Space is not fixed. It is dynamic, responsive, and deeply connected to energy and matter. The same universe that limits us also contains hidden pathways, subtle loopholes written into its very structure. Beyond warp, even stranger possibilities. Warp drives are only one possibility. Other ideas, like wormholes, quantum tunneling, and higher dimensional shortcuts, suggest that space might contain hidden connections between distant regions. These concepts push the boundaries of both physics and imagination, but they all share one common idea. The universe may be far more navigable than it first appears. What lies ahead? As we continue this journey, the question becomes even deeper. If space can be bent, if time can be stretched, if distance itself can shrink, then what truly limits how far we can go? In the next part, we will explore the ultimate boundary of the cosmos itself, the edge created not by speed, but by the expansion of the universe. A boundary that is slowly closing, and may define the final horizon of human exploration. The expanding universe and the final reachable horizon. Take a slow breath in, and gently let it go. So far, we have imagined traveling through space, pushing against the limits of speed, bending time, even warping space-time itself. But there is a deeper truth, one that changes everything. The universe is not static. It is expanding. And this expansion creates a boundary, not of technology, but of possibility itself. The discovery that changed everything. In the early 20th century, astronomers made a surprising observation. Distant galaxies were not standing still. They were moving away from us. The farther a galaxy was, the faster it appeared to recede. This discovery, closely associated with Edwin Hubble, revealed something profound. Space itself is stretching. Galaxies are not simply flying through space like shrapnel from an explosion. Instead, the fabric of the universe is expanding, carrying galaxies along with it. Expansion is everywhere. This expansion is happening in all directions, and from every point in space. There is no center. From any galaxy, the universe looks like it is expanding away in all directions. Even right now, distant galaxies are moving away from us at incredible speeds, some faster than the speed of light. This may sound impossible, but it does not violate relativity. Because again, it is not the galaxies moving through space faster than light. It is space itself expanding between them. The role of dark energy. For a long time, scientists believed that gravity might slow this expansion over time. But observations revealed something even stranger. The expansion is accelerating. This mysterious force driving the acceleration is called dark energy. We do not fully understand what dark energy is, but it makes up about 70% of the total energy content of the universe. And it is slowly, relentlessly pushing galaxies farther apart. The cosmic horizon. Because of this expansion, there is a limit to how far we can ever travel, even in principle. This limit is called the cosmic event horizon. It is the maximum distance from which light emitted now can ever reach us in the future. Beyond this horizon, galaxies are receding so quickly that their light will never reach us, no matter how long we wait. And more importantly, no matter how fast we travel, we can never reach them. A shrinking, reachable universe. At first, this seems counterintuitive. The universe is getting bigger, so shouldn't we be able to reach more of it? In reality, the opposite is happening. As expansion accelerates, more and more galaxies cross beyond the cosmic horizon. They fade away, becoming permanently unreachable. The observable universe, the part we can see, is vast. But the reachable universe, the part we can actually visit, is much smaller. And it is shrinking over time. The fate of distant galaxies. If you could travel instantly to a distant galaxy today, you might still be able to reach it. But if you wait long enough, that same galaxy may slip beyond the horizon. After that point, no signal, no spacecraft, no information of any kind could ever bridge the gap. It would be lost, not destroyed, but forever disconnected. This gives every destination in the universe an expiration date. The limits of even advanced civilizations. Even a civilization capable of near-light speed travel or warp technology would face this cosmic boundary. No amount of engineering can overcome the expansion of space itself. This is one of the most humbling truths in cosmology. There are regions of the universe that are fundamentally beyond reach. Not because we are too slow, but because reality itself forbids the journey. A future of isolation. Over billions of years, the effects of dark energy will become even more dramatic. Distant galaxies will disappear from view. Eventually, only the nearest galaxies, gravitationally bound to us, will remain visible. The rest of the universe will fade into darkness. Future civilizations may look into the night sky and see only emptiness, unaware that a vast universe once existed beyond their horizon. The quiet urgency of exploration. This creates a subtle but profound urgency. The universe we see today is richer and more connected than the universe of the distant future. Every moment, the cosmic horizon moves. Every moment, opportunities for exploration quietly vanish. In a sense, we are living at a special time, when the universe is still open enough to be explored. What this means for humanity. When we combine everything we've learned, a powerful picture emerges. Relativity allows us to stretch time and cross vast distances. Warp theories hint at bending space itself. But cosmic expansion sets an ultimate boundary. Even in the most optimistic scenario, humanity will never reach the entire universe. But that does not make exploration meaningless. It makes it precious. Looking ahead. So how far could a human travel in one lifetime? The answer is no longer just about speed or technology. It is about timing, about the structure of spacetime, and about the ever-changing horizon of the cosmos. In the next part, we will bring everything together, combining relativity, energy limits, and cosmic expansion, to map the true maximum journey a human could ever take. A journey measured not just in distance, but in the lifetime of the universe itself. Engines of the future. How could we actually get there? Take a slow breath in, and gently let it go. So far, we have explored the limits imposed by physics, speed, time, and the expansion of the universe itself. But now we arrive at a more practical question. Even if the universe allows long-distance travel, how could we actually build a ship capable of doing it? Because before we bend spacetime or outrun time itself, we must first solve a much simpler problem. How do you move forward in space? The problem with rockets. All spacecraft humanity has ever built rely on one principle. Push something backward, and you move forward. This is described by Newton's third law of motion. Rockets burn fuel and eject it at high speed, creating thrust. But this method has a serious limitation. You must carry your fuel with you. And the faster you want to go, the more fuel you need. But the more fuel you carry, the heavier your spacecraft becomes. This creates a vicious cycle. For interstellar travel, traditional rockets quickly become impractical. To reach even a fraction of the speed of light, a rocket would need more fuel than we could realistically store, or even launch from Earth. Nuclear propulsion, the next step. To go beyond chemical rockets, scientists have explored nuclear propulsion. Instead of burning fuel, these engines would use nuclear reactions to generate thrust. Projects studied by NASA and other institutions have proposed nuclear thermal rockets and nuclear pulse propulsion. One famous concept, Project Orion, imagined detonating small nuclear explosions behind a spacecraft, pushing it forward with immense cooler. This could, in theory, reach speeds of up to 10% of the speed of light. That's fast enough to reach nearby stars in decades, not millennia. But the engineering challenges and ethical concerns are enormous. Ion drives and efficiency. Another approach is not about power, but efficiency. Ion engines, already used on some spacecraft, accelerate charged particles to produce thrust. They generate very little force, but they can run for years. Over time, this allows a spacecraft to gradually build up high speeds. The spacecraft Dawn successfully used this technology to travel between asteroids. However, ion drives are still far too slow for interstellar journeys. They are like a gentle, continuous push, useful within a solar system, but not enough to cross the stars. Light sails, riding the photons. What if we didn't carry fuel at all? What if we used light itself? Light carries momentum. When photons strike a surface, they exert a tiny pressure. A light sail could capture this pressure and use it for propulsion. Projects like Breakthrough Starshot aim to use powerful lasers to push ultralight spacecraft to speeds of up to 20% the speed of light. At that speed, a probe could reach Alpha Centauri in about 20 years. But there's a catch. These spacecraft would be tiny, no larger than a chip. Scaling this technology up to carry humans is a challenge we have not yet solved. Fusion, the power of stars. A more ambitious idea is to use nuclear fusion, the same process that powers stars. Fusion engines could, in theory, provide enormous amounts of energy with relatively little fuel. Concepts like the Daedalus Project envision spacecraft capable of reaching distant stars within a human lifetime. But controlled fusion remains one of the greatest unsolved engineering problems. Despite decades of research, we have yet to build a stable, efficient fusion reactor suitable for propulsion. Antimatter, the ultimate fuel. If we look for the most powerful energy source known to physics, we find antimatter. When matter and antimatter meet, they annihilate each other completely, converting mass directly into energy. This process is described by mass-energy equivalence. Even a small amount of antimatter could produce enormous thrust. In theory, antimatter engines could push spacecraft close to the speed of light. But there is a problem. Antimatter is incredibly difficult to produce and store. All the antimatter humanity has ever created would barely power a light bulb for a few minutes. The challenge of survival. Even if we solve propulsion, another question remains. How do humans survive such journeys? Long-duration space travel introduces serious risks. Exposure to cosmic radiation, muscle and bone loss in microgravity, psychological stress from isolation, limited life support systems. Future spacecraft may need artificial gravity, closed-loop ecosystems, and advanced medical systems. In many ways, an interstellar ship would need to be a fully self-sustaining world. Automation and artificial intelligence. Because of these challenges, many scientists believe the first interstellar missions will not carry humans at all. Instead, they will rely on autonomous systems and artificial intelligence. Robotic explorers could travel vast distances without the need for food, oxygen, or protection from radiation. They could send data back to Earth, allowing humanity to explore the stars remotely. In a sense, our first journey to the stars may happen without us physically being there. A slow path to the stars. When we bring all these ideas together, a pattern emerges. There is no single solution. Instead, there is a gradual path. Chemical rockets, nuclear propulsion. Nuclear propulsion, light sails. Light sails, fusion and antimatter. Fusion, perhaps, one day, warp technologies. Each step brings us closer, but also reveals new challenges. What this means for our journey. The dream of interstellar travel is not impossible. But it is not easy. It will require breakthroughs in physics, engineering, and perhaps even our understanding of life itself. And yet, something remarkable remains true. Even with technologies we can imagine today, humanity could already begin reaching the stars, slowly, carefully, step by step. Looking forward. So how far could a human travel in one lifetime? We are getting closer to the answer. We now understand the limits of speed, the flexibility of time, the expansion of the universe, and the engines that might carry us forward. In the next part, we will explore a deeper question. What happens to a human mind and body during such a journey? Because traveling to the stars is not just a physical challenge. It is a profoundly human one. The human journey, mind, body, and time among the stars. Take a slow breath in, and gently let it go. So far, we have explored the physics of reaching the stars, speed, energy, and the vast structure of the universe. But there is another question, quieter and more personal. What happens to a human being on such a journey? Because traveling across space is not just a technological challenge. It is a test of the human body and the human mind. The fragile body in an unforgiving environment. Human beings evolved on Earth, under gravity, protected by a thick atmosphere and a magnetic field. In space, all of that disappears. Beyond Earth, astronauts are exposed to intense radiation, high-energy particles that can damage cells and DNA. On missions aboard International Space Station, astronauts already face increased radiation levels. But interstellar space is far more dangerous. Without proper shielding, long-term exposure could significantly increase the risk of cancer and other diseases. Life without gravity. Gravity is something we rarely think about. But in space, its absence changes everything. In microgravity, muscles weaken. Bones lose density. The body begins to change. Astronauts must exercise daily just to maintain basic physical health. On a journey lasting years or decades, this becomes a serious challenge. Future spacecraft may need to simulate gravity using rotation, creating a centrifugal force that mimics the pull of Earth. But even that is only an approximation. The silent challenge of isolation. Physical survival is only part of the story. The human mind is deeply connected to environment, routine, and social interaction. Long-duration missions can lead to loneliness, anxiety, cognitive fatigue, changes in perception of time. Imagine looking out of a window and seeing nothing but darkness and distant stars for years. No new landscapes, no fresh air, no natural sounds. Only the quiet hum of a machine carrying you through the void. Time perception in deep space. On Earth, time is structured: days, nights, seasons. In space, these natural cycles disappear. Astronauts must rely on artificial schedules. But over long periods, the human brain can begin to lose its sense of time. Days blur together. Weeks feel like moments, or like eternity. And when combined with relativistic travel, time becomes even more strange. A traveler might experience only decades, while centuries pass on Earth. The psychological weight of one-way journeys. Many interstellar missions may not allow for a return. A traveler could leave Earth knowing they will never come back. Everyone they know, everything they recognize, will eventually be gone. This creates a profound psychological burden. It is not just exploration. It is separation from home, from history, from humanity as it once was. Can humans adapt? Despite these challenges, humans are remarkably adaptable. We have lived in extreme environments, deep underwater, in polar regions, in orbit around Earth. Over time, the body and mind adjust. Future generations of space travelers may be trained from birth for life in space. They may see the stars not as distant points, but as destinations, artificial worlds in space. To support long journeys, spacecraft may need to become more than vehicles. They may need to become worlds. Closed ecosystems could recycle air, water, and nutrients. Artificial environments could simulate nature, trees, water, even weather. Living spaces might be designed to reduce stress, maintain mental health, and create a sense of home. In such a ship, the journey itself becomes a place to live, not just a path to somewhere else. The role of technology in human survival. Advanced technologies could help overcome many biological limits. Genetic engineering to improve radiation resistance. Advanced medicine to repair cellular damage. Neural interfaces to support mental health. Artificial intelligence companions to reduce isolation. These ideas are still emerging, but they point toward a future where humans are no longer limited by their original biology, becoming something new. At some point, we must ask a deeper question. If we change the human body and mind to survive space, are we still the same species? Interstellar travel may not just expand our reach. It may transform what it means to be human. Future travelers could be fundamentally different, adapted for long lifetimes, extreme environments, and deep space existence. The emotional reality of the stars. Beyond physics and biology lies something even more subtle. Emotion. To leave Earth is to leave behind everything familiar. The sky, the oceans, the feeling of wind, the sound of life. Even if we reach distant stars, we carry with us the memory of a world we can never fully replace. Looking forward. So how far could a human travel in one lifetime? We are beginning to see the full picture. It is not just about distance. It is about endurance, adaptation, and identity. In the next part, we will explore the ultimate strategies humanity might use to overcome these limits entirely, extending life, pausing time, or even escaping the need for a human body at all. Because the journey to the stars may not only change where we go, but what we become. Beyond the human, consciousness, immortality, and digital existence. Take a slow breath in and gently let it go. We have explored distance, time, technology, and the limits of the human body. But now we arrive at the most profound question of all. What if the true path to the stars is not about moving the human body, but leaving it behind? Because the greatest limitation in interstellar travel may not be physics. It may be us. The problem of the human lifespan. Even with relativistic travel, even with advanced propulsion, one constraint remains. Human life is short. A few decades, perhaps a century. But the universe operates on timescales of thousands, millions, and billions of years. To truly explore the stars, we must either travel faster or live longer, extending life beyond biology. Scientists are already studying ways to extend human life. Advances in medicine, genetics, and biotechnology suggest that aging itself may one day be slowed, or even partially reversed. Cells could be repaired. DNA damage could be corrected. Diseases could be prevented before they begin. In theory, a human lifetime could stretch far beyond what we know today. But even centuries may not be enough for deep interstellar journeys. Cryosleep, pausing time. Another idea is not to extend life, but to pause it. Cryogenic sleep, or suspended animation, would allow travelers to enter a state where biological processes nearly stop. Time would pass, but the traveler would not experience it. This concept has not yet been achieved for humans, but research continues. If successful, a journey of thousands of years could feel like a single night's sleep. But this raises a strange question. If you skip the journey, did you truly experience it? Uploading the mind. Now we move into even more radical territory. What if consciousness itself could be separated from the biological brain? The idea of mind uploading suggests that the structure of the human brain, its neurons, connections, and patterns, could be mapped and transferred into a digital system. A human mind could exist inside a machine. No fragile body. No need for air, food, or gravity. Only information. Digital travelers. A digital consciousness could travel in ways a biological human never could. It could be transmitted as data, copied, backed up, restored. A spacecraft carrying digital minds could be incredibly small, efficient, and resilient. Time would no longer be a limiting factor. A digital mind could wait thousands of years and experience it as a moment, or choose to experience it fully. The question of identity. But this idea introduces a deep philosophical problem. If you copy your mind, is that still you? Or is it a new version of you, one that only believes it is the original? Your biological body would remain behind. Your digital version would continue. Which one is truly you? This question has no clear answer, and yet, it may become one of the most important questions humanity ever faces. Becoming immortal. If consciousness can exist independently of the body, then in theory, it could become immortal. A digital mind could survive as long as its hardware is maintained. It could move from system to system, adapting to new environments. It could explore the universe without the fear of death. But immortality brings its own challenges. Would time lose its meaning? Would memories become overwhelming? Would identity begin to fade or fragment? To live forever may not feel the way we imagine. A new kind of civilization. If humanity embraces digital existence, civilization itself could change. Instead of physical expansion, we might see informational expansion. Consciousness spreading across space as data. Entire societies existing inside vast computational systems. Exploration would no longer require ships filled with people. It would require signals, traveling at the speed of light. The merging of human and machine. The future may not be purely biological or purely digital. It may be something in between. Humans could gradually merge with technology. Neural implants enhancing thought, artificial memory storage, direct brain-to-computer communication. Over time, the boundary between human and machine could disappear. We would not abandon our humanity. We would redefine it. The emotional cost of transcendence. But even if we overcome death, even if we become something greater, there is something we may lose. The feeling of a heartbeat, the warmth of sunlight on skin, the fragile beauty of being alive in a moment that will never return. Mortality gives meaning to experience. Without it, existence may feel very different. Looking toward the final question. So how far could a human travel in one lifetime? At this point, the question itself begins to change. Because if a human can become digital, if a lifetime can be extended indefinitely, then the limits of travel are no longer tied to distance or time. They are tied to definition. What does it mean to be human? In the final part, we will bring everything together. Physics, technology, time, and consciousness. And we will answer the question not just scientifically, but existentially. How far can we go before we become something else entirely? The final horizon. How far can we truly go? Take a slow breath in and gently let it go. We began this journey with a simple question. How far could a human travel through space in one lifetime? But now, after everything we've seen, that question feels very different. Because the answer is no longer just about distance. It is about time, about physics, about the nature of being human itself, the limits we cannot escape. The universe has rules. The speed of light cannot be surpassed. Energy is never free. Space itself is expanding. No matter how advanced we become, there will always be boundaries. Distant galaxies will drift beyond reach. Some destinations will remain forever inaccessible. There is a horizon we cannot cross. And yet, we are not as limited as we seem. Within those limits, something extraordinary exists. Through relativity, a human lifetime can stretch. A journey that lasts thousands of years for the universe could feel like decades to the traveler. Through technology, we may extend life, protect the body, and build worlds among the stars. Through imagination, we have already gone further than any spacecraft. The universe does not make things easy, but it does not make them impossible. The true distance of a lifetime. So how far could you go if you remain bound to Earth? Your journey is measured in kilometers. If you travel through space with advanced propulsion, your journey is measured in light years. If you ride the edge of relativity, your lifetime could carry you across the entire Milky Way. And if you leave behind the limits of biology, your journey may no longer have a clear end at all. But every path has a cost. To go far, you must leave something behind. Time, home, the people you love. A traveler moving near the speed of light may return to a future where everything they knew is gone. A digital mind may explore the stars, but never again feel the warmth of a living world. The greater the distance, the greater the separation, the quiet truth of exploration. In the end, space travel is not just about reaching new places. It is about understanding our place. We are small, fragile beings in a vast universe. And yet, we are also the part of the universe that can ask questions, that can wonder, that can dream. Every step outward is also a step inward. A universe that is slowly closing. Right now, the universe is still open. Galaxies are visible. The night sky is full. But over billions of years, expansion will carry most of them beyond the cosmic horizon. Future civilizations may never see what we see today. They may not even know that other galaxies exist. We are living at a rare moment in cosmic history, a moment when the universe is still within reach. So, how far can we go? As far as physics allows. As far as technology can take us. As far as we are willing to change. Maybe that means traveling to nearby stars. Maybe it means sending our minds across the cosmos. Maybe it means becoming something entirely new. The answer is not a single distance. It is a spectrum of possibilities. And perhaps, that is enough. Because the true measure of our journey is not how far we travel, but that we travel at all. That we look up at the night sky and choose to move toward it. That we refuse to remain still in a universe that is constantly changing. A final thought. Somewhere, far beyond what we can see, there are stars that will never know we existed. And yet, here we are, aware, curious, reaching outward. The universe may be vast and silent, but through us, it has found a way to wonder about itself. Thank you for being here, Crescent Moon. If this journey helped you relax, think, or see the universe in a new way, consider subscribing to Sleep and Learn. There are still more mysteries to explore, more quiet journeys to take. Until next time, take a slow breath in, and gently let it go.